Welcome back, friends. This is the another session on analog modulation, that is pulse analog modulation, unit number 6. Okay, in the last session, we have studied the pulse analog modulation, analog techniques, and now in this section, we will study the digital modulation technique, that is pulse code modulation, which is commonly used, okay, also known as the PCM technique. Okay, it is first introduced by Alec Reeves in the year of 1937. Before that, PCM it is not used commercially until 1950s, when the invention of the transistor made it viable. Although it was used by Bell Labs during the Second World War for secure communication link for encrypted voice communication between Roosevelt and Churchill. Okay, the important part is that PCM is a type of pulse modulation like PM, PWM or PPM, but there is an important difference between them. This PM, PWM or PPM are analog pulse modulation technique, whereas PCM is a digital pulse modulation technique. That means the PCM output is in the coded digital form, okay, not in the analog form. It is in the form of digital pulses of constant amplitude, width and position. Okay, it is constant amplitude, width and position, not variables. Okay. Therefore, the information is transmitted in the form of code word. Information is transmitted in the form of code word. Hence, because of this, this will be used in Bell Labs during the Second World War for secure communication links for encrypted voice communication between Roosevelt and Churchill. Here, now, the most commonly used digital modulation scheme is nothing but the pulse code modulation. In that in that one, the available range of signal voltages, that is analog signal, is divided into levels, number of levels, and each level is assigned a binary number. The number of levels available depends upon the number of bits used to express the sample value. Okay, and the number of levels, it is given by q, that equal to 2 raised to n, 2 raised to n, where n is the number of bits to represent each sample. It consists of basically three steps to digitize an analog signal. The first one is sampling, then it is quantization, and then it is binary encoding. These three steps are very important. Okay. So this is the block diagram of pulse code modulation. This divided into three segments. That is, one is your PCM encoder, then it is channel, transmitted channel, and then it is receiver. So we'll study one by one. That is, first one is transmitter. Now in the transmitter side, the input is source of continuous time message signal, or also known as your input signal x of t or analog signal. This analog signal is applied to a low pass filter. The work of low pass filter is to convert this analog signal into the band limited to its maximum frequency FM or its a maximum bandwidth W. Hence, it will not affect by aliasing effect. Okay, so it follow the sampling theorem or Nyquist criteria. Then this signal, band limited signal, is applied to the sampler. The sampler is convert the analog signal into the discrete form by using sampling theorem. This discrete form signal is applied to a quantizer. The work of quantizer is nothing but the approximation. Okay, it approximate to a number of, it approximate to a voltage level. Okay, and then the output of quantizer is applied to a encoder that will encode the quantized levels in the form of binary signals. And this binary signal is nothing but the PCM signals. Okay, this PCM signal is applied to a channel path, or it is also known as the transmission path. These three blocks, that is sampler, quantizer and encoder, done by a one single device, that is known as analog to digital converter. In a simple manner, this is A to D converter. Okay, so when this signal, encoded signal, is passed through a transmission path, we use regenerative repeaters because the output is somewhat noisy. To remove that noise, we use the regenerative repeater. One important thing is that these regenerative repeaters are placed close each other. Number of repeaters are used. Okay, hence the noise level has to be maintained, minimized. Okay, means the output of transmission path, it is nothing but the clear pulse code modulated signal. That is the work of regenerative repeater, and this regenerative repeater is applied to a receiver side. The work of receiver is exactly opposite to the encoder side. So this is final channel output applied to a regeneration circuit. Means we have to boost the amplitude and voltage level of that signal. Then applied to a decoder part. The work of decoder is nothing but the exactly opposite to analog to digital converter, and that is done by using D to A converter, that is digital to analog converter. And then it is applied to a reconstruction filter because we have to back to get the original analog signal, and then finally applied to the destination. So this is the work of pulse code modulation. That is the introductory part of pulse code modulation. Explanation of block diagram. This is the simple work of PCM encoder only. PCM encoder, that is the input to PCM encoder is your analog signal, then it is applied to the sampling. This is the sampled signal, that is pulse amplitude modulated signal. It is applied to a quantizer, and this is the quantized signal, means approximate to a certain level, and then this each level is converted into a binary data, that is 1 1 or 0 0, 1 1 0 0, depending on the number of bits is used to represent each sample. If we use n equal to 3, then this sample level value is represented by 3 bits. Okay, so this is the PCM encoder. Now this is the sample output, graphical output of PCM encoder stages. That is analog signal, then it is a sample, natural sampling, and then it is quantized signal. Okay, this amplitude is quantized to some certain approximate level, and then after that sample to sample and hold signal. Now we are going into the details of quantization process. Okay, so what is meant by quantization? So before that, we explained that quantization is nothing but the approximation. Okay, so how exactly done with this one, we'll understand here. Now consider this is the analog signal. Okay, this is a peak to peak value is 4 to -4. Let us consider it's a peak to peak voltage level is plus or minus 4, that is plus 4 to -4. Okay, so this analog signal, uh, after sampling, it is divided into number of stages, number of levels. So the number of levels is represented by q. So here we will be considering number of levels are 8. Okay, so when we consider number of levels of 8, then we can represent each sample by using 3 bits, that is n is equal to 3. So hence from this formula, q equal to 2 raised to 3 then equal to 8. So if we consider 8 number of levels, then number of bits to represent each sample is n equal to 3. Okay, so first this will be understand. Then this analog signal, this number of levels is divided into 8. Okay, so from this we need to calculate the step size of analog signals. Divided to the number of steps, then we need to calculate the step size. Okay, so to calculate step size, this is represented by S. The formula is high voltage level minus low voltage level divided by number of levels. So here peak to peak voltage level is nothing but 4 to -4. If you consider plus 4 high voltage level minus low voltage level, that is -4. 4 minus of -4, 8 divided by 8, that equal to 1. Okay, so this signal step size is 1 1. So here consider from this 0 0 to 0 here to 1, then it is 2 3 4. Similarly for lower side, here also -1 -2 -3 -4. So in that step level we need to mark one decision threshold line, just like in between 0 to 1 we mark this 0.5 line. This is known as decision threshold line. Similarly between 1 to 2 it is 1.5 decision threshold line. Downside in between 0 to -1, this minus 0.5, it is decision threshold line. Okay, so we mark all decision threshold lines and assign a number to them according to the number of levels. So here assigning number of level, that is from downside it is q0, then q1, then q2, then q3, q4, q5, q6. so on q7. The number of levels are 8, so it is 0 to 7. The number of levels are 8. Okay. So this q0, q1, q2, q7 are known as decision threshold line. Decision threshold line means, suppose here these are the sample values, that is 1.3, 3.6, 2.3, 0.7, so on. These are the sample value of the signal. This is given. Okay. So here let us assume this is 1.3. So this 1.3 it is nearer to greater than 1, it is nearer to 1.5. So whatever value between 1 to 2, 1 to 2, it will be approximated to 1.5. This is decision threshold line. So here 1.3, it is approximated to nearest quantization level, that is 1.5. Okay. So this 1.5 is nearer than the zero point 0.5, so it is approximated to 1.5. Similarly, this 3.6 quantization value is nearer to 3.5, approximated to 3.5. Similarly, here 2.3 is the sample value. What is the nearest quantization level is 2.5, okay, than the 1.5. 1.5 is far, but 2.5 is near, so this 2.3 is approximated to 2.5. Similarly, 0.7 is approximated to 0.7. So remember that the difference between the actual value and the nearest quantizer value, it is known as quantization error. It is known as quantization error, and we need to keep quantization error as minimum as possible. And this can be done by using the number of increasing the number of quantization level. Okay. So this is the another part here. Now this is approximated level, nearest quantization level is 1.5, 3.5. Now we assign number to each level, that is 0, 1, 2, 3, 4, 5, 6, 7, that is decision threshold levels. Okay. So now this is 1.5, this 1.5 assigned number is 5, this 3.5 assigned number is 7, this 2.5 assigned number is 6. Okay. Similarly, so on 4310. Now this code number is converted into binary, okay, by using 3 bits, so this 5 represented in binary using 3 bit is 101. This 7 is represented in binary by using 3 bit is 111. Similarly, this 6, 4, 1, 0, 0, 0, 0, 1. So this is the encoder output. This is the PCM encoder output. Now this output is converted into the pulse form, pulses, that is 101. If you represent this 101 in the pulse form, is nothing but 1, then it is 0, then it is 1, 101, 111, all these are 111, 110, 110, 101. So this is 1 and then 0 and then 0, 0, 0, 1. So this pulse final output of PCM encoder. This is the pulse output of PCM is transmitted through channel or applied to a regenerative repeaters in the transmission path. So this is the process of pulse code modulation encoder. Okay, pulse code modulation encoder. Now we will understand some of the limitation of the pulse code modulation. So in PCM system, n number of binary digits are transmitted per sample. Hence, the signaling rate and channel bandwidth of PCM are very large. Okay. Also, encoding, decoding, and quantization circuitry of PCM is complex. So these are the some limitation. But though these are limitation, it will be commonly used in digital modulation technique. Okay. So these are some examples of pulse code modulations. For more details, you can refer the Simon Hacking book or Tauben Selling book for mathematical analysis. Okay, but for introductory part, this much is sufficient. Hence, we complete the digital communication part or digital pulse code modulation technique as per the requirement of university syllabus. Okay, hence in this way we have completed the unit number 6, that is pulse analog modulation. Okay. For more detail, you can refer the reference book. Thank you.